All right, how's everyone doing today? Cool. So I am running a super experimental setup that I dreamed up last night. So I'm going to need some feedback at a few points to know if my audio is working and if my proper screen is sharing and stuff like that. But I have two laptops and three monitors and two Zoom sessions and all kinds of stuff wired together with the goal of being able to run this Aldec software in a way that makes it very clear to see on screen, but also lets me record it while running it on a Windows system. So my primary goal is that what we do in class today comes across very clearly on the screen and so on, instead of having the camera pointed at a laptop and so on. My secondary goal is to get a good quality recording of it, but I'm willing to sacrifice that in exchange for, being able to have people actually see what's going on and not deal with weird colors on the screen and stuff like that. So hopefully all of this works, but it's experimental. So my goal for today is to go over Verilog. And we can talk about any questions up front on the lab, lab 6, or the homework, and so on and so forth, or other material. But I'm planning to spend, hopefully, most of this morning talking about Verilog. So if there's questions on Verilog, we'll probably get to them, but you can ask those too if you want to talk about them up front. So any questions we want to start with? And can somebody open a mic and just say testing or something to let me make sure that part of this is working?
Testing.
Awesome, thank you.
Perfect.
All right, well let's just jump in then with Verilog. So I'm working largely with this intro to Verilog quick start guide that's been on Canvas and we've talked about a little. And let me remind you what the basic setup is. Mostly when we write Verilog, we're going to mainly work with a single module. Now, just like programming languages, we can make a module. We can make a second module. We can include those in the third module. We can take all of that, put it in another module. Just like we have functions that can call other functions in a programming language. Most of what we do here, we're going to stick to just one module. So like one main program, for example. And so we'll usually say, module name, a list of arguments, and a semicolon. And these arguments are the things that are either inputs or outputs. They can be bidirectional. We won't worry about that. We'll just have inputs or outputs. And so we specify for each of these whether it's an input A or an output B, and so on. And we also need to tell the system what kind of thing is this. And for the first part of this, we're just always going to say these are wires. So they're like, things that you would plug into a proto board to connect to these pieces of a chip, for example. So we'd probably say wire A, wire B, and so on. And then we can put in the actual guts of what we want our module to do. And then we end with the keyword end module. And the main thing we're going to do inside here are these assignment statements. And we can say assign something equals something. So for example, if we assign, B equals A and C, we're asking to create a module that performs an AND operation. In this case, it takes these two things as inputs, it generates that as an output. And this is not representing a sequence of steps like in a program, right? So modules represent hardware. So this is a description of this. Right? It's an AND gate, but it's a piece of hardware. If this was a function written in Python, it would do something like, hey, when we call name with A, B, and C, take the values of A and C, calculate the AND of those, set B equal to that. And if we had more assignment statements, those would get executed after, and so on. That's not what Verilog does. It's not a programming language. It's a way to describe hardware. And that's the number one thing you want to keep in mind, right? I spent a number of years off and on trying to figure out Verilog. That was the one thing that suddenly made it click. It's not a program. It's a description of a piece of hardware. So anytime we're writing Verilog, somewhere in our minds we can keep a picture of what this hardware we're describing looks like. And if you don't have a picture in mind, if you're thinking of a series of steps, you're on the wrong side of this sort of mental divide between software and hardware. And this may seem fairly obvious. It'll get less obvious as we move forward. So let me start with a module. And I'll use our more common names. A and B will be inputs, X will be output, and X will be just the AND of A with B. And I want to run through an example of using this Aldec tool. You've got the quick start guide. Hopefully you've gone through that and typed in some Verilog code and simulated it. Let's do that one more time as a class, and we'll do that a little bit slowly. And then we're just going to keep using that to develop more types of circuits, more types of modules using these assign statements. And then we'll move into the really fun part of Verilog, which is what we call behavioral Verilog, where we no longer have to design with AND gates and OR gates and truth tables, but we can say, you know, make me a widget that does such and such, and it will do it for us. So this is where we get kind of experimental. So I am logged in as a guest, and I'm going to start sharing my screen from a different window. And so let me do this. All right.
All right, we can see it.
Okay, cool. Now my other goal in doing this is that I don't like spam everybody's name onto a YouTube video with the recording. So let me see if I can do this. Well, there we go. All right. Okay. We'll deal with that. I'll take out names. All right. So, this should be showing my Windows laptop. Okay, this is a little goofy. So let me go ahead and run this. So hopefully at the least people have downloaded and installed this software, um, and are able to get it to start and so on and so forth. One person I think is using OS X and did not have access to a Windows machine or chose not to, and so there's different tools you can use for this. So there's a totally different tool suite called Icarus. It's open source. It's lightweight. It seems to be bug free. I think it's actually superior for what we're doing to the Aldec tool. But the Aldec tool is more kind of the sort of tool you'd encounter in industry. It does more things, but what we need it to do is a tiny little piece of its capabilities. But just be aware, there are lots of different ways to do Verilog development and simulation. This is one of them. If you learn the Aldec tool, you've seen something similar to what you might use, on the job if you were doing this as an engineer. But Icarus and GTK Wave are another pair of tools that will let you do the same things for this course. And so there's just lots of options. All right, so let's start with a brand new design. So let me do the one thing that it's described in the documentation, but in case you didn't do it, come down to Tools and Preferences. So this is under one-time setup. So go to Tools, come under Preferences, go under Simulation. So expand this if it's not expanded, and then click on Access to Design Objects. And normally this box is checked, which says Limit Read Access. Uncheck that, and then check these three boxes. If you don't do that, then none of the other stuff works. And you start getting complaints every time you try to simulate. But you only have to do this once unless you later go back and reinstall the software. So I've already set that up, so I don't have to worry about that. All right, so File, and let's do a new workspace. And remember, every circuit you try to design should be in its own workspace. All right, so I'm going to call this and demo 1. I'm typing in the wrong window though. And demo 1. All right. Another suggestion from the documentation: keep your file names clean. No spaces. No weird characters. Don't count on uppercase, lowercase being significant because this is Windows, and so on and so forth. Make life easy, right? If you specify a path, don't put spaces in the path, right? It's 2022. Those things should not be problems, but they are sometimes. So don't add extra work. Keep everything sort of as straightforward as you can. And mostly we're going to take defaults. There's one or two exceptions. So here we're just going to go ahead and say next. Here's our one big exception: default language Verilog. So instead of VHDL, say Verilog. Everything else we can just sort of take the defaults. We need to specify the name of the design. I'm going to use the same name as the workspace, as the module, as everything else. So this is going to be and, I can't even remember what I call it, demo 1. Still typing in the wrong window. Alright, so and demo 1. And then I'm just going to say finish. And now we've got a bunch of nothing. Alright, so I'm going to right click on and demo. I'm going to say new, and I'm going to say Verilog source. So this is going to give me an editor window where I can type in my Verilog code. I'm going to go through a wizard that basically lets me specify the system diagram. So go ahead and say next. And then for the name of the source file, again, I'm going to do and demo 1. And now I can specify input and output ports. So I'm going to say new, put in the name of my first port, which is A, that's an input. I'm going to say new, put in the name of my second port, that's an input. I'm going to say new, put in the name of my third port, but change this to output. And you can see I've got a system diagram here. A and B go in, X comes out. And I'm going to say finish. And just like that, I've got a bunch of Verilog. How did I get where?
I missed one step. You said now we have a page called nothingness, and then you said right click on what was it?
Oh, so I right-clicked here where it says and demo 1, and I said new Verilog source.
Okay, thank you.
Welcome. All right. So Verilog, right? Things that start with 2 slashes are comments, just like most programming languages. So this is sort of boilerplate information about me, about this file itself, and you can customize this. You can add a description in here, and this is Notepad, right? It's a very unglorified editor. So demo of Verilog code for an AND gate. I'm going to be really careful about changing any code that was generated. I can change these comments, but this code, like the timescale and the module name and so on, I'm going to leave those as is. And then down here it says enter your statements here. This is where I'm going to actually type my code that describes what I want to do. So I'm going to do a single assign statement, assign x equals a and b. And that's my program. But this could be longer. It could have lots of things going on in there, and we're going to complicate this as we go forward. But we're always going to write our stuff right inside here. This is defining the name of the module. This is listing the inputs and the outputs, and then this is kind of the action items. All right, so this should be the Verilog for a simple AND gate. So we got to do a few things. First thing, I'm going to click on Design and say Compile. And I'll get a message down here in tiny little print. The source is compiled without the switch. That's okay. Compile success, 0 errors, 0 warnings. That's what you're after. So that green line right there. All right, now we got to simulate. If you do any of these steps in the wrong order or you click the wrong thing, I don't know how to fix that. So if I deviate from these steps, I just start over, right? I'm sure there's a way to fix it, but I actually don't understand the inner workings of this tool well enough to be able to navigate, different paths to the same point. And this is one way to deal with software interface packages and so on, is find a way from where you are to where you want to get and just stick to that. Right, so I'm going to do exactly the same steps every single time, and if I mess up, I'm just going to start over again. So I'm not going to give you, 20 different ways to do this and so on. So I want to do a simulation now, right? I've written some Verilog. I've compiled it. My Verilog is correct. I want to see what it actually does. So this is the simulation part. So there's a software piece inside this Aldec tool that will let me set the inputs of this module to different values and observe the outputs. And that takes the form of timing diagrams. So that's what we're about to do now. We're going to simulate the behavior of this module. Okay, first thing, File, New, Waveform. And again, this is all in that Aldec Quick Start Guide. So we're just going through this as a class. So File, New, Waveform, and I get this picture over here. And then waveform simulation, initialize simulation. All right, first time you do that, you get this little pop-up. It says select the top level design. Because again, modules can be put inside other modules, so it wants to know what is it you want to simulate. We only have one module, so it's an easy choice. So I'm going to say OK, and I'm going to click the little plus sign to expand this. And down at the bottom, I'll see the name of my module and demo 1, and it's got a little gold star next to it. I'm going to click that and say OK. And as soon as I do that, over here I see my inputs and outputs for that module. Okay, So here's where my timing diagrams are going to appear, this box in the middle. And over here is where I can list which signals I want to see timing diagrams for. So I'm going to click and drag these into here. And I did figure out how to make these larger so we can actually read these more easily. So I've got A, B, and X. And it's telling me the value of these right now. So Z means undefined. A is an input. I haven't told it what that input value should be. That's undefined. And since A and B are undefined, and this is an AND gate, we don't know what the output is. And so it's showing the output of X as just being X. X means unknown. So if you're seeing Z's and X's, you haven't set up the stimulation of your inputs. All right, so this is our next part. Add stimulus for the inputs. All right, so I'm going to right-click on A, and I'm going to say Set Stimulus. I'm going to take the default here and just say OK. And now you get this really cool window that basically says, how would you like to change the input of A across time? And we have some options. The option we're going to use mostly is just a clock. We're going to say, hey, I want to hook a clock up to input A. But we could also specify a counter. We can specify a formula which says at this time do this, at that time do that. We can make it random. We can read it from a file, so on and so forth. I'm going to set input A to be a clock, and I'm going to set it to 20 nanoseconds. I'm going to right-click on B, say Set Stimulus, take the default, and I'm going to make this a clock, but I'm going to set the period to 40 nanoseconds. Okay, why am I doing this? I want to go through all combinations of A and B. This is an AND gate. I want to know if it works. So I want to set the inputs to both 0, 0, and then 0, 1, and then 1, 0, and then 1, 1. If I set A and B to both be a clock with a 20 nanosecond period, they would both be low, and then they both go high, and they both go low, and they both go high. And that would let me check, inputs of 0, 0 and inputs of 1, 1. But I also want to check 0, 1 and 1, 0. So I'm setting A to change very quickly, and B to change half as quickly. So A and B are going to be low, and then A will go high. And then A will go low and B will go high. And then A will go high while B is high, and then they'll both go low. And that's going to get me through all 4 combinations. And this is a standard trick when you're trying to do your simulation. Set up your clocks with different frequencies. And if you make each clock, double or half the frequency of another clock, you'll get this set of different combinations. So we'll see this when we get the timing diagram. All right, so I've set up the stimulus. I should be all set to go. So up here, there's this little box that says 100 nanoseconds. Immediately to the left is a button that, if I hover on it, it says run for. Except it doesn't want to talk to me. But this button says run for 100 nanoseconds. I don't want to use these other buttons. These buttons say run forever and break my simulation. So I want to use this button right here, run for 100 nanoseconds. So I'm just going to click that, and bingo, I've got some data. So the input A, you can see that every 20 nanoseconds it goes through a cycle. It starts off low, after 10 nanoseconds it goes high, after another 10 it goes low. That's one cycle. And this point right here is 20 nanoseconds. Here's another cycle. It's low, it goes high, it comes low again. 40 nanoseconds, it's done 2 cycles. So A is changing, 0, 1, 0, 1, 0, 1. B, we set the period to be 40 nanoseconds, so it stays low for 20 and then goes high for 20. And after 40 nanoseconds, it's completed 1 cycle. So we can see combinations. Here A and B are both 0. Here A is a 1 and B is a 0, and you can see the values over here, 1 and 0. Here A is 0, B is 1, and here A and B are both 1. And we can see the output x. And sure enough, x is 0, 0, 0, but when a and b are both 1, x is a 1. That's an AND gate. Success. So that's a start to finish example of entering in code for a Verilog module, compiling it, simulating it, setting up stimulus, generating waveforms. And if your goal for the day was to create an AND gate, we're done. We can go home, we can do what we want. It's going to be a nice day, we can go outside and so on. But if we want to do other things, right, we're going to repeat these steps. And so let me hit this stop button. It says this ends the simulation. And let me come back here and let's change our code. So let's make an OR gate. Alright, this is where the rapid development cycle starts to kick in. So I'm going to come back to, there's tabs up here, right? So just like a tab browser. Here's my Verilog code, ndemo.v. Here's my simulation window. So I'm going to click on ndemo.v, and I'm just going to change this from an ampersand to a pipe. Pipe means OR. Alright, I'm going to say design, compile, and it tells me no errors. I'm going to come back to my waveform here. And if I just try to hit the simulation button, I'm going to get more of these undefineds. So let me stop this. So here's the trick you have to do. You have to come up here and right click on stimuli set and say set as active. This took me 2 days to find. Okay, so when you want to do another simulation, come over here, and if you don't see this stimuli window, come under Windows, window list. Nope. How about view? Stimuli. Yes, thank you. Alright, so right click on this and say set as active. And now if I say run the simulation for 100 nanoseconds, I think I unchecked it. Alright, we've got a simulation window again, and guess what? This is an OR gate. So both inputs are 0, the output is 0. And I'm just left clicking anywhere in here to move this cursor. So here my inputs are 1, 0, output's 1. Here's a 0, 1, output is 1. Here's a 1, 1, output is 1. Alright, let's try an XOR gate. So we're going to set x equal to a and not b, or not a and b. I've got a typo in here, but let's go ahead and compile it anyway, and let the compiler tell us. So I've got an error here. It says unexpected token, right parentheses. So I'm missing a left parentheses here. So I'll go ahead and put that in, and I right-clicked on here to compile, but let's be consistent. Design, compile, no errors. Let's come back here. Let's set this as active. Maybe it is active. Alright, so here's our simulation. And you can see both inputs are 0, output's 0. Both inputs are 1, the output is 1. But if exactly one input is a 1, the output is a 1. Sorry, both inputs 1, output's low. If one input is a 1, the output is a 1. So this is an XOR gate. This is also, a gate that tells you if the two inputs differ. So 1 and 0 or 0 and 1, the output should be 1. If the two inputs are the same, both low or both high, the output is a 0. Alright, good time for questions.
Could you go back through creating design workspace?
Mm-hmm.
Or the timing workspace?
So let's close this out. When I close this tab, it always asks if you want to save. I just say no. So File, New Waveform. That's the first step. A waveform is always hard for me to find. And then Simulation, Initialize Simulation. And then the first time you do that, it says, tell me what the top module is. You'll expand the little box with the plus sign next to it, choose the name of your module, and then you'll see this window here with these signals over here, and then just drag these in. And then go ahead and set up stimuli. We already have stimuli set up, but we could create new stimuli. So I could set this to be random. And when you set up a random input, you can specify the period. So let's change this every 10 nanoseconds. And you also specify a seed. The seed is what starts the random number generation. So just put in some arbitrary number. And I'm going to set up B. I'm going to right click, say set stimulus, and say OK, and I'll make that random also. And I'll do that with 10 nanoseconds, and I'll put some different random number in the seed. And now when I run this simulation, A and B should change randomly every 10 nanoseconds. And so if you wanted to do kind of a less controlled test, right? You can set this up and get different combinations, not only of A and B, but different sequences of how those change. When we use clocks, A and B always change in the same way. But when we set them up random, right, we don't know if they're going to go from high to low or something else. And so you can also verify that in all cases this seems to be doing the proper exclusive OR function. And you can do a lot of things in here. I'm gonna say mess around with it, right? Just like Tinkercad, you can read the documentation for it. There's all this thick documentation, but go and mess around with it, right? So a lot of things are standardized in user interfaces today. So if I hold down Control and hit the scroll wheel on my mouse, I can zoom, right? Just like a browser. Zooming happens around wherever your cursor is. So if I want to zoom around the beginning, I can point my cursor near the beginning of my waveforms, hold down Control and press zoom. I can hold down Shift and scroll wheel to scroll left or right, and so on and so forth. Alright, you can print these. And so in your homework and your lab, you want to include waveforms as well as source code. You can do a screen copy, but you can also, there should be a print option inside here. And you can print to a PDF file. And you can change the background color and set the background color when you print and so on and so forth. Mess around with it. Okay, and if you need help, ask me. But seriously, get in the habit of jumping in and playing around with these tools. It's the fastest way to learn how to use these things. And there's scroll bars if you prefer, to scroll with that. But most things let you shift and scroll wheel. to scroll, and then control scroll wheel to zoom. Alright, there's a cursor. It will tell you what the current time is, so 25,202 picoseconds. That's 25.202 nanoseconds. And so these numbers up here are nanoseconds, and you can see current values X, Y, Z. All right, other questions? All right, let me see if I can... Well, I don't know why your name always comes up. All right, so let me turn off my share. And let me switch this. All right. So we can do this to, design circuits the way that we've done this with proto boards. We can make a truth table, we can do a K-map, we can simplify and come up with, big circuits with lots of gates, and so on and so forth. And if that was all that Verilog let us do, it wouldn't be terribly useful. It would save us from physically inserting wires into proto boards. But, it would still be a lot of work. And, your traffic light control circuit had several proto boards, several chips, lots of wires, lots of potential for mistake. And I mentioned that's not really the way that we go about designing circuits in practice. So, I don't know if this is an official term or not, but I use the term behavioral. Verilog. I feel like I can't spell behavioral today. The idea of this is Verilog is able to some degree understand what our goal of our circuit is and create a circuit in response to that. And so, for example, suppose we want to do a 2-bit adder. Now, you've done this in a lab. It was a lot of work. It was pages and pages of circuit diagrams and big K-maps and things like that. But what does our system look like behaviorally? We have an input A, which is 2 bits. So I'm using this little slash with a 2 to mean a 2-bit input. So we have an input A and an input B. Those are the numbers we want to add. We have an output, which I can call sum, which is going to be 3 bits. And our goal is, our sum should be equal to A plus B. And I'm writing the word plus instead of a plus sign so we don't think it's an OR operation. But our goal is to add these two numbers together as integers, produce a 3-bit sum. And we can do this in Verilog pretty easily. So let me go back to our Aldec tool. All right, let's close this out. So I'll stop the simulate. I'm just going to close the whole workspace. So I'm going to say close workspace. It says it'll stop the simulation. I'm okay with that. I don't want to save anything. So we're back to the beginning now. This is as if we had just started up the Aldec tool. Alright, so let's say file, and we'll say new workspace. And I'll call this an adder, or an add test. So again, take the defaults, create an empty design, switch this to Verilog, click through the rest, add test. Alright, and I'm going to right click on here. I think you can also do this from the file menu and say new Verilog design. I'm going to stick to right click on the name add test and say new and say Verilog source. And say next. Alright, so name of the module is going to be add test. Alright, so let's make an input. I'm going to call my first input A. I want to be a collection of 2 wires. So over here I can say array index. So if you've done programming languages, you know what an array is. It's a variable that has multiple values to it. And so this is like an input that has multiple values associated with it. 2 values in particular, A1 and A0. So I'm going to add indexes. I'm going to make this an array from 1 to 0. So this part over here, right, I'm saying this top index is 1, the bottom index is 0. So we have A1, A0, right, which is what we called these things when we were doing truth tables and so on and so forth. A1 is the most significant bit by default. A0 is least. Alright, this is an input. I'm going to go ahead and say new, and let's do the same thing for B. And we'll make B an array from 1 to 0. And I'll say new, and then I'll make my output sum. And sum is going to be an output, and we want it to be 3 bits. So my array index is going to go from 2 to 0. And so here's my system diagram. A bracket 1 colon 0. That means there's 2 lines for A. Same for B. Sum bracket 2 colon 0. I've got 3 lines for sum. Sum 2, sum 1, and sum 0. Alright, and I'm going to go ahead and say finish. There's my magic chunk of Verilog code. Enter your statements down here. And again, this is going to be a single assign statement. Assign sum equals A plus B. And Verilog knows how to add things. So it will synthesize an adder using, you know, all the stuff that we know how to do. It knows how to do also. It will figure out, you know, the truth table for addition. It will figure out the values for each output, make K-maps, minimize, come up with logic gates that implement that.
Question.
Yeah.
Will you have used the plus sign as an or sign? Would that ever come into effect in Verilog?
So Verilog makes it a little confusing because a plus means addition, and in or you have to use that pipe symbol. So, pipe means or, and plus means add. And just for completeness, this means and a tilde means not. And I think a caret means an XOR, but I'm not positive about that one. So here we're definitely saying let's add A and B together. So let's design compile. And compiled with no warnings, let's go ahead and simulate. So 2 steps, file, new waveform. And then simulation, initialize simulation. It'll ask us to name the top module. Going to extend this or expand this and pick add test and say OK. And now we've got our signals down here. I can highlight all of those and drag them in one step if I want. And now there's a little plus symbol next to these symbols. I can expand these, and I can see that I've got A1 and A0, and I've got B1 and B0. And I've got some 2, some 1, and some 0. Alright, so let's leave these unexpanded for the moment. Alright, so we need to set up stimulus. So I'm going to right click on the signal name, and if you right click in the wrong spot, right, if my cursor changes to this big arrow, I'm not able to right click. Well, I can't get it to do it again. If it changes to that symbol, I'm too high up. So make sure your cursor just looks normal and right click. And you can move these things around. I can click and hold down my mouse and drag this somewhere else. So I'm going to right click on A. I'm going to say set stimulus. Alright, well here I don't want to use a clock because I have 2 input bits that I want to change. Alright, someone said in chat caret is an XOR, so that's cool. Thank you. Alright, so I'm going to use a counter here. And I'm going to say, hey, every 20 nanoseconds, let's change our count. We're going to start our counter at 0. We're going to count up by 1. It's going to be a binary counter, and I'm going to show my count value in decimal. So this is just going to change my 2-bit A input from 0, 0 to 0, 1, 1, 0, 1, 1, and then back to 0, 0. Alright, so that's what my input A is going to do. And now let's set up a stimulus for input B. And I'm going to make this a counter also. But I'm going to change the speed at which it counts. Again, I'm thinking I want all possible combinations. So here's my idea. I'm going to let B start off at 0. I'm going to let A count 0, 1, 2, 3. And then when A goes back to 0, I want to increment B. So B will increment to a 1, and I'll let A go 0, 1, 2, 3. And then I'll let B increment to a 2, and I'll have A go 0, 1, 2, 3. And so we'll get all our combinations like that. So I want B to increment every time that A rolls over from 3 back to 0. Well, A is counting every 20 nanoseconds. So it's going to be at 0, and then at 20 it's going to go to 1, 40 it's going to go to a 2, 60 it's going to go to 3, 80 it's going to go back to 0. So I'm going to set B up to count every 80 nanoseconds. And I'll leave the rest of this as is. And now let's go ahead and run our simulation. And we'll run it for a few steps. And let's come back to the beginning. And what do we got? Over here we've got 0 plus 0 equals 0. Over here we've got 1 plus 0 equals 1. 2 plus 0 equals 2, and 3 plus 0 equals 3. At this point, B increases to 1. We've got 0 plus 1 equals 1. Here's our most favorite result. 1 plus 1 equals 2. And then 2 plus 1 equals 3, and 3 plus 1 equals 4. And I'm looking at this, you know, in terms of the waveform. This is a 3. This is a 1. And the sum is equal to 4. But I can also read the values over here. 3 plus 1 equals 4. I'm shifting and scroll wheeling to slide my view over. Here's 0 plus 2, 1 plus 2, 2 plus 2 is 4, 3 plus 2 is 5. And here's 0 plus 3 is 3, 1 plus 3 is 4, 2 plus 3 is 5, and 3 plus 3 is 6. And then it will wrap back over again. After 320 nanoseconds, we go back to 0 plus 0. So these first 320 nanoseconds, right, the first 4 cycles of B show me all my possible values. And if I scroll wheel with the control button, I can zoom out. And this is a nice little synopsis of the behavior of the circuit, right? This would be a great screenshot to put in a lab report if I was doing a lab report with a 2-bit adder. because it's pretty easy to read. You know, for example, 2 plus 2 right here is equal to 4. So I'd probably move my cursor out of the way, take a screenshot of this, or use the print option, and I can put that in my report. It's also instructive to expand, say, A and B, and we can see exactly what it means when we say A is equal to 0 or 1 or 2 or 3. Over here, A is equal to 2 because A1 is a 1, A0 is a 0. So 1, 0, that's binary for 2. Over here, we've got a 1, 1, that's binary for 3. That's the sense in which A is equal to 3. And so this can help us, you know, sort of think about inputs to a module and how we can take multiple inputs and treat them together as, you know, say an integer value. And so over here we're doing 3 plus 3. Well, A1 is a 1, A0 is a 1, so A is equal to 3. Down here, B1 is a 1, B0 is a 1, so B is the number 3. And if we expand the sum, we can see right here the 3 sum bits, starting with the most significant bit, are 1, 1, and 0. Right? 1, 1, 0, that's the binary representation of 6. So this would also be a nice timing diagram I would put in my lab report, because it shows, you know, the individual signals, A1, A0, B1, B0, right? Those 4 input bits and 3 output bits, and it shows the value of each bit. All right, well, let's tweak this. Let's go back to our code, and let's make a subtractor. So let's come into our add test, and let's just change this and say sum equals A minus B. We'll design compile. We'll come back to our simulation. And let's go ahead and set this to active. It looks like I have to at least start the simulation to set this to active. I think I can also do simulation, initialize simulation. So stop this, initialize the simulation, and then I should be able to set this to active. And then run this. And let me unexpand these, and let's just see what's going on here. So 0 minus 0 is 0. 1 minus 0 is 1. 2 minus 0 is 2. 3 minus 0 is 3. That's what we would expect, right? 3 minus 0 should definitely be 3. But take a look at this next row. 0 minus 1 is equal to 7. Right, our output is 1, 1, 1. All 3 of our sum bits are equal to 1. Why is 0 minus 1 equal to 7? Super duper bonus bragging rights. Why is 0 minus 1 equal to 7? I'm going to go back and delete all of those because I don't really want to spam your name. What is 0 minus 1? Yeah, okay. Someone said it in chat, right? What is 0 minus 1? It's equal to minus 1. Well, how do we represent minus 1 in binary? We've got a 3-bit sum. How do we represent minus 1? Well, 0, 0, 1, that's positive 1. Take the complement of every bit, add 1. This is how we represent minus 1 in 2's complement. And that's what our simulation is telling us. The output is 1, 1, 1, which in decimal is just, you know, good old 7. And so we've built a circuit that does subtraction really for almost no work. Right? All we had to do was say, you know, assign sum equals a minus b. I wasn't sharing my screen, right? So 0, 0, 1, that's positive 1. Complement all the bits, add 1, that's negative 1. And if you're computer science, right, you'll dream about patterns of consecutive ones. This is probably the second most common bit pattern we'll encounter in working with, you know, low-level computer architectures and so on. It's just a big long string of ones, and it's often minus 1, or it's the biggest integer you can represent. So it pops up a lot. And if you're looking at hex numbers, this will be like, you know, 8 Fs, for example. Well, that's just 32 ones. So we'll recognize those quickly eventually. All right, let me go back to screen share. So my challenge with this window is that if I try to make it full screen, I can't move it onto the other window. Okay, I'll just edit out names later. All right, so let's just eyeball our other values, right? So 0 minus 1 is 7. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. That's all as we would expect. And then over here, 0 minus 2 is 6. Well, what is 6? It's 1, 1, 0. And if you look at that as a 2's complement number, you'll find out that's the 2's complement representation of minus 2. So 0 minus 2 is minus 2. 1 minus 2 is minus 1 again. 2 minus 2 is 0. And so on. And then finally, 0 minus 3 is 1, 0, 1. That's 2's complement for minus 3. And if I right-click on sum, I can say notation, and I can say let's represent this as a 2's complement number. Oh, that didn't do what I wanted. Okay. Property sum. Let's put this in decimal as assigned 2's complement number. So now I can see this as 0 minus 2 is negative 2, 1 minus 2 is negative 1, and so on and so forth. 1 minus 3 is negative 2, and so on. So you can right-click on these signals, come down to properties, and change how they're presented. So you can show them in binary, octal, decimal, hexadecimal. You can make them unsigned, and so on and so forth. Again, there's tons of stuff this tool will do, including changing radix. And your best bet is to explore, right? Right-clicking brings up context menus for most of this, and properties exposes all of these different options. And there are display options, so I can change the color, I can change the height, I can make it bold-faced, and so on and so forth. One of the challenges with using tools like, Aldec HDL is that they can do so much, and you can spend, 6 months just learning the tool and never actually write any Verilog. Or you can try to write Verilog and not get anywhere because you don't know the essential steps you need. So that quick start guide on Canvas is intended to kind of get you from nothing to the bare minimum steps that you need to do what we've been doing here so far. Enter in Verilog, compile it, make a simulation window, drive the inputs with stimuli, and look at the timing diagrams. But that's really just kind of a starting point. All right, other questions? Otherwise, we're going to do a 5-minute break and then come back and then shake this up. All right, so let's do a quick break. Let's come back at 9:08, and we will talk about behavioral Verilog and continue this idea of describing what we want our circuit to do, but in the context of sequential machines. So things that have a notion of state, a notion of memory. So we'll come back in about 5 minutes, and we'll pick up from there. Leave my microphone open.
Yeah.
Yeah, the lecture is being recorded as far as I know. Like I say, it's a very strange setup I've got running, but it looks like it's recording. If it ends up not recording, I'll go ahead and cut a short video that just kind of reviews this stuff, and I'll post that.
Hey, Professor.
Yeah.
I believe Zoom actually records the lecture or the entire Zoom. So I'm not sure how it would work, but you could maybe just pull their recordings.
I thought about that. Yeah, thanks. So Zoom will let you record. The challenge I run into is that I don't want to show like students' names or chat windows or things like that, and invariably those things pop up, and I want to be able to go back and edit those out and so on. And so I'm trying to do my usual recording on this end, but that is another option, and I think students have the option of recording the lecture themselves, and that can also work if you just want to make sure you've got your own copy. It's a work in progress, but that is a good suggestion. Alright, let me get this back. Alright, I believe we're back. Let me bring this volume down a little bit. Alright, let's see. That's sharing, that's good to go. Alright. Alright, so let's talk about event-based circuits. So, the idea here is we want to create circuits with clocks. So AND gates, OR gates, XOR gates, 2-bit adders, 2-bit subtractors, those are what we call combinational circuits. Those are the first half of ENGR250 circuits. And then we started talking about circuits with clocks. And these were sequential circuits, things that had a notion of state or a memory of past behavior. And the sort of most classic example of a sequential circuit would be a counter. So a counter, like, you know, the 7493 that you've used, every time the clock ticks, it adds 1 to its value. So it counts from 0 to 1 to 2 to 3 and so on. And that's classic sequential behavior because, you know, what's the clock? 0. What's the output? I have no idea. Right? It's whatever it was a moment ago. Now the clock changes from 0 to 1. What's the output? I have no idea. It's whatever the value was a moment ago plus 1. So with a counter, we can't just look at the current value of the inputs. We have to look at the history of the circuit and say, oh, the output was, you know, 101, that's a 5. Now the clock tick, the output's going to be 110, that's a 6. And so we can design sequential circuits using flip-flops and combinational logic and making a state transition table and doing all of that stuff we did in homework 5 and homework 6. But again, in Verilog, we can describe what we're after behaviorally, and Verilog will do the hard work for us. The compiler will do the hard work for us of coming up with a circuit that achieves our end goal. So let's make a counter. So I'm going to say File, New Workspace, and I'm going to call this Count 4. We're going to make a 4-bit counter. So I make an empty design. I'm going to switch my language to Verilog. I'm going to call it Count 4. finish. I'll come over here, I'll right click, I'll say new Verilog source. I'll say next. I'll call it count 4. And now we got to specify inputs and outputs. Well, I know I want an output. So I'm going to call my output, you know, X, and this is going to be an out direction. I want X to be 4 bits. So my array index is going to go from 3 to 0. So X3, X2, X1, X0. That's my 4-bit output. I'm also going to add a clock. So I'm just going to call this clock. That'll be my input. And normally for a counter, that's all I need. Just a clock. Every time the clock ticks, I'll just bump up the count by 1. But I'm going to do something else. I'm going to add a reset line. And this is partially just a nod to the realities of simulation. If I don't put in a reset line and I build a physical counter, it'll work. I don't know what value it will start at, but it will start at some value, 1011 or whatever. And every time the clock ticks, it will increment. But the simulation tool doesn't understand that when you power a flip-flop, it's got a value. It might be a 0, it might be a 1, but it has a value. The simulation tool will say, I don't know what the value is, so if I add 1, I still don't know what the value is. And it'll just show us unknown for every output. So we're going to add a reset line, and this is a good practice in general, because, you know, when you power up a circuit, you'd like to be able to put it into a known state. So this is kind of forcing the system to an initial state. So I'm going to make an input called reset. And I'm going to say finish. Alright, so I've got a circuit. It has 2 inputs, a clock input and a reset input, and a 4-bit output called X. Alright, so here comes the next keyword, which is always. And always is the keyword that exposes all the magic of Verilog. So I'm going to say always at positive edge clock begin. I'm going to put begin on the same line just to match my documentation. Alright, so what does this mean? This is designing a circuit which will not do anything until this signal clock changes. The positive edge means it changes from a 0 to a 1. It increases. If I said negative edge clock, then all of this would happen when the clock dropped from 1 to 0. So always at pos edge clock. Do the following when the clock ticks from 0 to 1. And I'm going to put some if statements in here. If reset. Then I want to set out equal to 0. Yeah.
We do not have a semicolon at the always line.
Correct, yeah.
Should we have one? Or
No, and I can't explain why. I don't know. We'll try putting it in. I don't think it will break anything. In which case we can go ahead and put that in to be consistent. But end module does not take a semicolon. And begin does not take a semicolon. But that's in the minds of the people who came up with this language. But we'll try putting it in after this and see if it breaks anything. Alright, so I have an if statement, if reset, and I could say if reset equals 1, but just like in C, right, if you say if variable, it means if the variable's non-zero, it's true. So if the reset signal is asserted, I'm going to set my output equal to 0. else I'm going to set my output equal to output plus 1. And then I'm going to put an end statement, which ends my begin. And then I'm going to have my end module statement to end my whole module. And I prefer to indent in a way that oh, my output is called X, isn't it? Thank you. So indenting in Verilog is totally for the user, right? It does not care if I have a bunch of spaces in the beginning here or if I have everything slammed over to the left. So I'm indenting, this should be an input. I'm indenting just to make it easier for me to look at this and say, hey, all of this is inside my always block. All of this is inside my module definition, and so on. So maybe I would indent all of this, but not like that. All right, so this is almost going to work. We need one other keyword, which is reg, R-E-G, versus wire. And I'm going to change X from saying a wire to saying it's a reg. And usually reg means I want a flip-flop. I want something that can remember a value. Alright, so here's the next big conceptual challenge. Remember, we're not writing code. We're not listing a series of steps. We're describing a piece of hardware. And this always block has to be interpreted as some kind of hardware, some picture of a circuit that we could draw on paper. And the way we can interpret this is, hey, we're going to have some kind of flip-flops, you know, with this clock feeding the clocks, and these flip-flops are going to be positive edge triggered. And what we want our circuit to do is, hey, every time the clock ticks, we want to check the value of the reset line. If it's asserted, we want to set X to 0. Otherwise, we want to set X equal to X plus 1. So let's go ahead and simulate this, see what it does, and then let's look at what this circuit might synthesize into. So let's try compiling this. So I'll do design compile, and got a warning because I had an X somewhere. X is supposed to be an output. So let's design compile that. Alright, that compiled, 0 errors, 0 warnings. Let's simulate it. So file, new waveform. Simulation, initialize simulation, pick your top level module, which is just going to be count 4. I'm going to drag in my reset signal, my clock, and X. Alright, well my clock is pretty straightforward. I'm just going to set this up to be a clock. So I'll clock at, let's clock at, I don't know, 50 nanoseconds. And my reset signal, I want to set my reset high in the very beginning, and then I want to set it low. So I'm going to click on reset, set stimulus, and I'm going to say, let's use a formula. Maybe. And so let's add something. Let's set it to a 1 at the beginning. And then let's set it to a 0 after 100 nanoseconds. Alright, so my reset should start off high for 100 nanoseconds and then drop low. My clock's just going to keep ticking the whole time, and we'll look at what the output does. So let's go ahead and run this simulation, and we'll step it a few times. And let's zoom out and go back to the beginning. So let me set a cursor here. So interesting behavior, right? Our reset is high, our clock is low, our output is unknown. If I look at the bit values, they're all represented with a line on top and a line on bottom. That means it doesn't know what the value of x is. So it's just showing me an x for unknown, right? That's because the reset takes effect when the clock ticks. So when the clock is low, reset is high, we don't know what the output is. But right here, the clock ticks from a 0 to a 1. That's when the reset line is sampled. It says resets 1, let's set the output to 0. So we see a 0 in the output here. And then the clock goes low, nothing changes. The clock goes high again, nothing changes. Why? Because reset is still 1. And then the clock goes low, reset goes to a 0. So now the reset line is no longer asserted. And the next clock tick from 0 to 1, guess what? Our output changes to 1. And then the next clock tick from 0 to 1, our output changes to 2. And then it'll change to 3 and 4 and so on. And so you can see it counts from 4, 5, 6, 7, 8 all the way up through F. And then in the next clock tick it rolls back over to 0. And if we expand the 4 bits of X, we can see our standard pattern that we see sometimes when we draw our outputs from a 7493, right? Bit 0 is changing very rapidly, bit 1 is changing half as rapidly, bit 2 is changing more slowly, and bit 3 changes the slowest. And so when we say our output is C, it means the 2 most significant bits are 1, they're high, and the 2 least significant bits are low, 0 and 0. And there's our 1, 1, 0, 0 over there. And again, we could come here under properties and we could say, let's display this number in binary. And now we'd see the actual binary code for each value of X. And so on and so forth. So there's a counter. And the Verilog code really couldn't be simpler. It's basically 2 statements. If the reset signal is asserted, set your output to 0. Otherwise, set your output to its current value plus 1. Alright, so let me go ahead and talk about what this is actually doing. So our code looked something like this. If reset out is 0, else out is out plus 1. Alright, so first thing I want to mention, this notation, a less than sign followed by an equals to make this thing that looks like an arrow, It's really, really important that you use that instead of an equal sign. Now for the assign statement, combinational circuits, we just say assign x equals, a and b, or a or b, or a plus b. But for these things inside always blocks, we've got to use this funny equal sign, this less than sign followed by an equal. And so this looks something like always at positive edge clock begin, and then an end. Alright, this less than equal, this is called a non-blocking assignment. Equal is called a blocking assignment. And I'm going to say don't use this. Alright, we'll see an example next when we do a shift register of why we want a non-blocking versus a blocking. But let's talk about this in some more detail first, and then we can make sense of this funny assignment statement. So remember, this is a piece of hardware that we're describing here. It's not a set of code. We're asking to create a circuit with the following behavior. When the clock ticks on the positive edge, when it changes from 0 to 1, we want the output to be either set to 0 or set to the current output plus 1. So what might that hardware look like? So we're going to have some sort of set of flip-flops. Let's say 4D flip-flops. So there's a 4-bit input and a 4-bit output. But 4 flip-flops, each a D, single bit. And they're triggered with the positive edge of a clock. So our clock is going into the input of each of those flip-flops. And when the clock ticks, we want our D value to either be the current value plus 1, or we want it to be equal to 0. So we might do something like this. Let's take our output Q. And let's feed it into an adder. So we'll have 4 bits going into A, we'll have 4 bits going into B. The value going into B is 0, 0, 0, 1. The value going into A is the current value coming out of the flip-flop. And then the sum coming out, well, this thing is just, the current value of the flip-flops plus 1. Because we're adding 1 to it. And then maybe we would take this and we'd run it through an AND gate. And we would take our reset and invert that and put that into our AND gate. So this is, 4 AND gates. And we might build a circuit that looks something like this. So what's the idea? If reset is 0, then this inverted reset is a 1, and this AND gate just takes whatever the input is, passes it to the output. So if reset is 0, this whole thing basically takes the current value of the flip-flops, adds 1 to it, sets that to the D inputs. When the clock ticks, guess what? Your output becomes your output plus 1. But if you set the reset line to a 1, this inverted reset becomes a 0, and whatever the current value of the flip-flops are, each of those bits ANDed with a 0 produces a 0. All of our D inputs will be 0. And when the clock ticks, our output becomes 0. Now, is this what the Verilog compiler will come up with? I don't know. It would probably use a series of 2-to-1 multiplexers here to choose either a 0 or the corresponding bit from our adder. And it may do something, different from a straight 4-bit adder. It might use some special logic. But this is the effect of what it comes up with, right? But this is very different from, a Python program where we say, if this, do that, and so on, right? It's not code, it's hardware. And the key idea of a hardware definition language like Verilog is these things that look like programs are actually descriptions of circuitry. Now, we don't need to know what this circuit looks like. That's the idea of Verilog, is we simply describe what behavior we want. Hey, we want to know, if the reset is 0, reset the output. Otherwise, increment the output. All right, let's modify this counter. So let me do some funny business with my screens again. All right. Let's make a different kind of counter that can count either slowly or quickly. So let me modify my code here and add a fast input. All right, so let's add a fast option. So I'm going to say comma fast. And the idea is if I set this fast input to 1, I'm going to count by 3s instead of counting by 1s. And it's going to take one more line of code. So if reset is asserted, then I'm going to set x equal to 0. Else if fast, x is x plus 3. Else x is x plus 1. And so I've got one more input up here, fast. I'm going to set that up as an input. So I'll say input fast, wire fast. So let's design compile and come back to our waveform. Let me stop this and let me say simulation, initialize simulation. So now I can move my fast signal into here. And let me, how should we drive fast? Let's just drive fast with a clock. And let's just change this every 500 nanoseconds. I don't know if this is a good way to do this or not. So let me set this as active. Let me set that as active. I knew I was going to get into trouble. Alright, let me try this again. Set stimulus. I'm going to add this to stimulus 1. I'm going to get in trouble. Nope, that worked. Alright, I'm trying to modify my signals here. I should not be doing this. So I'm going to close this out. And I'm going to go back to File, New Waveform. Simulation, Initialize Simulation. And I'm going to drag all of these in here. I'm going to put my reset signal up at the top. Put my fast signal and my clock and my X. So reset, set stimulus. I'll use a formula. I'll start it off at 0. And then after 100 nanoseconds, sorry, I'll start it off at 1. And then after 100 nanoseconds, I'll change it. So I'll start at a 1, I'll change it to 0. Our fast signal, let's drive this with a clock. And I'll do that every 500 nanoseconds. And our clock, let's just go ahead and use a fast clock here. And let's just do this every 20 nanoseconds. I'm making this up as I go. But you know, it's like when we first drew timing diagrams. It's a question of how should I set the inputs in order to exhibit the behaviors I'm interested in this circuit. So, you know, I want to do a reset in the beginning to get the thing started. And I'm just going to have it count for a while. And then we're going to change the fast signal to a 1 and have it keep counting and see if it counts quickly. And then bring the fast signal back to a 0 and see if it counts slowly again. So I'm setting these up accordingly. And so I'll go through some simulation. I'll zoom out, come back to the beginning. So again, while the reset line is high, the count is a 0. Once the reset line drops to a 0, every time the clock ticks positive, we count up. So we count from 0 to 1, 2, 3, 4, 5, 6, 7. And then at this point, our fast signal got asserted, and now we counted from 7 to 10 to 13, back to 0, 3, 6, 9. And you can see my circuit's counting quickly. There's 12, there's 15, 2, 5, 8, 11, 15, and now my fast signal drops, and it counts slowly from 14 to 15, 0, 1, 2, 3. Again, one extra line of code. If my fast signal is asserted, count by 3, otherwise count by 1. And so what circuit have we designed? Well, you know, we had our flip-flops and the outputs carried around and went back to the inputs. And we said, you know, if reset was asserted, then let's change that set of D inputs to be a 0. Well, we'd add more logic and say, hey, if reset is not asserted, but fast is asserted, you know, instead of putting a 1 into our adder, let's put in a 3. Or maybe, you know, we have one adder that increments by 1 and another adder that increments by 3, and we use some kind of 2-to-1 selector based on the fast signal to choose which of those adder outputs we want to feed back to the D inputs. But we don't really need to worry about that as Verilog designers. We just say, hey, here's what I want to have happen when the clock ticks. If we're saying reset, clear the count. Otherwise, if we're saying count fast, add 3 to the count. Otherwise, add 1 to the count. And once we are in this mindset, we can start developing code really quickly, developing circuits really quickly. So if we wanted to make an up-down counter, well, we could have an input called up. And we'd say if up equals 1, x equals x plus 1, otherwise x equals x minus 1. We could add a pause button, and we'd say, you know, if up equals 1 and pause is equal to 0, then set x equal to x plus 1. And then if our pause input was asserted, this x gets assigned to x plus 1 would not happen, and our count would be paused. And so there's examples of this stuff in the textbook. There's examples in that intro to Verilog document. And once you're fluent with the HDL tool, right, doing these same, 7 steps or whatever we keep doing again and again, you can start making changes here and doing experiments. So let's add a semicolon here, see if that changes anything. So design compile, that seems to compile fine. And we can come back here, we can say, let's stop this. Let's set this as active, and let's run the simulation. And maybe I'm on set 2. I got myself in trouble now because I didn't reset before. Right? So now, we can see it's still doing the same thing. So when our fast is 1, it counts by 3. When our fast is 0, it counts by 1s. So yeah, quick experiment. We can put semicolons at the end of our begin statement. No harm done. We can also do things like if we wanted to do more than one thing in our reset, we could say begin. And we could say set x equal to 0, and then we could say end. And so if you know Python, Java, C, right, begin, end are kind of like the curly braces. They can be used to block off a set of statements that we want to have executed. All right, let's make a shift register. You've done this in hardware. You did this in experiment 1 when you made your delay circuit. You made a 2-bit shift register. And so let me come back to my camera once more. So what does a shift register look like? Normally it's a bunch of flip-flops. The output of one feeds the input of the next. They're all clocked in unison. And the idea is whatever signal you put in here eventually trickles out here and trickles out here and trickles out here. So we can do 2 things with shift registers. One is we can create a delay circuit. That was experiment 1 in lab 6, right? We have an input change from 0 to 1. It takes a few seconds, 2 clock ticks for that output to appear on this output here. The other thing is we can remember a series of inputs by storing them inside here. So let's say I input a 1. I'm going to have a 1 here and a 0 and a 0. And now I input a 0. Well, this 0 is going to move down here. This 1 is going to move down here. This 0 is going to come here. And now I have another 1. This 1 will move here. This 0 will move here. This 1 input comes here. Right? I have in my flip-flops a memory of the last 3 input values. And so we can use shift registers to remember sets of inputs. So this is one of the experiments in lab 7. This 5 of 16 detector, well, you need to remember 16 events and then see if 5 of them were equal to 1. So you need a shift register. Rather than describe a set of flip-flops with the output of 1 feeding the input of a next, we can use Verilog to describe the behavior of a shift register. And it basically works like this. I'm going to have, let's just say, 8 bits. So I'll do shift register 7 through 0. And here's the idea. I'm going to have some input which goes into shift register 0, goes into shift register 1, goes into shift register 7, and that's our output. The Verilog code for this is straightforward. whatever the input is, I want to copy it into SR bracket 0. So I could say SR bracket 0 takes the value of in, SR1 takes the value of SR0, SR2 takes the value of SR1, and so on. We got 5 minutes. Let's see what we can do. Alright, I'm going to make a totally new workspace. I'm going to close this workspace. That's another thing. Make sure you only have one open workspace at a time. Otherwise, you can get confused about what code is going with what module and so on. So I'm going to close all my workspaces. I'm going to say File, New Workspace. I'm just going to call this SR for Shift Register. Create an empty design. Going to use Verilog. Going to call this SR for the design name. I'm going to say Finish. I'm going to right click on SR. And I'm going to say New Verilog Source. Source file is going to be called SR for Shift Register. And we are going to have an input called in, and we're going to have an output called out. Pretty clever. Alright, I'm going to need a register. So I'm going to make a register called SR. I'm going to say register bracket 7:0. And I'm going to say always at positive edge clock begin. Alright, so what do I want to do when the clock ticks? I'm going to take SR bracket 0 and I'm going to give that the value of whatever my input is. I'm going to take SR1 and give that whatever the value of SR0 is. And now I'm just going to do some copy and paste. This is the problem with notepad style editors. Alright, so my input's going to get copied to SR0, SR0 will get copied to SR1, and so on. And my output will get copied to SR. Actually, I can do an assign statement. So this will be the end of my always block, and I'm just going to assign output equals SR7. Alright, I don't know if this is going to work or not. Let's find out. Let's compile. And I need to specify a clock. So let's compile. No errors. Let's try a quick simulation. So we'll go File, New Waveform, Simulation, Initialize Simulation. Select the top level module, which will just be SR. There's our input, there's our clock, there's our output. Alright, so I'm going to do the following. I'm going to set up my clock to just be a plain old clock. So we'll toggle every 40 nanoseconds. And my input, I'm just going to make this random. So I'll make this random with a period of 40 nanoseconds. And let's see what we get. Let's also put SR in here. Well, my input's not very exciting, is it? Well, I blew my input bit. We are out of time. Let me see what I can do. One more try. All right, so we've got some stuff happening now. Let's go ahead and look at our shift register. So here's the behavior you typically get with a shift register, right? Our input, let me close this. Our input is a 1, and when the clock ticks, that 1 gets shifted into that first flip-flop. And you can see each time the clock ticks, it moves from one flip-flop to the next. And my input stayed high, right? And so we started shifting in these 1s. At this point, my input went to a 0, and so the value of SR0 was a 0, and that starts shifting through. But if we close this out and we just look at input versus... Let me run this a few more steps. Just look at input versus output, right? Here's an input that drops low. Here's where that appears on the output. It's 8 clock ticks later. Here's another low, followed by a high, followed by a low. It came on the output here. There's low, followed by high, followed by low. But it's a total of 8 clock ticks from input to output. And at any given point in time, the 8 values in our shift register correspond to the last 8 input values. Alright, that's a horrible place to end lecture, but we're way past time. But that's the setup of a shift register. And one thing to think about is if this was a C program or a Python program, this would copy input to SR0, which would then get copied to SR1, which would then get copied to SR2, and in the end, all of these would be equal to input. But this is not a procedural program. This is a piece of hardware. And it's saying at the clock edge, make these following assignment statements. And if you go back and you think about your circuit for experiment 1 lab 6, the same thing is happening there. At the clock edge, the first Q goes into the second D. The external input, the switch, goes into the first Q. And it's not that switch runs through all the flip-flops and becomes the final output. Everything moves one step because they all happen at the clock edge. And this does not happen if you use equal signs. If you use equal signs, you'll get a totally different behavior. Alright, so that's technically everything you need for the homework and the labs, but we didn't have a lot of chance to really explore this one very deeply. So do what you can with the lab. Come by lab hours tonight, or office hours tomorrow for help with that, and then same thing for the homework. But do what you can. Ask questions. Right. This is a big subject without a lot of time to go over it. So do the best you can. Definitely ask questions, and don't worry about the grade. Worry about the concepts. Right. And I'll be grading these fairly gently. All right, we're out of time. Thanks for sticking around. Have a great afternoon. I will see you next time. All right, bye.